Welcome back, everybody. So this is a series that I'm doing to learn the programming language Rust. What I'm doing is I'm learning Rust, the programming language, and then in parallel I'm building a program that will do something that I think is pretty neat. And so what I'm doing is writing a Rust program that will be able to parse and display a commonly used data format in astronomy. And so that data format is called FITS. It was invented by NASA a long time ago. It's quite an old data format, but it's really commonly used. For example, the Hubble Space Telescope uses it. And so at least when NASA makes those images available, it wraps those up in FITS files. And so what we've been doing over the last few videos is writing this Rust program that you can see here in Visual Studio Code. Last video we made good progress. We got to a point where we had a sort of high-level coverage of parsing all the major structures that we care about in a FITS file. So that was the header and the data unit, and then also pulling out the extension data. And we have a very simple sort of loop here that goes through and matches the state and does different parsing depending on what it's looking at. But there were lots of assumptions in this code. For example, we were making assumptions about the dimensionality of the data. We were making assumptions about the size of those dimensions. And anyway, and we were doing that to try and get started. Today what we're going to do is really sort of take a more generic approach to this. We're going to generalize how we look things up in the header, which contains metadata about the file. And then we're going to also get to a point where we can start displaying beautiful images, hopefully. We'll get there. But again, I had some feedback. So there's a couple of people that are giving me really constructive feedback. They are more experienced Rust programmers, and so thank you to those couple of people as well. Again, what I'm going to do is take their feedback on board and improve this program. It's pretty simple to do that. I think I'm slowly getting better at Rust. I've got a long way to go, but I'm getting better and I'm understanding a little bit more about it. So if we sort of start from the top down, one of the bits of feedback was that I didn't need to use this extern crate statement. So if I look at this, I'm actually using a crate called byteorder, and that's because the binary data or the data, the stream of the sequence of bytes in these FITS files is big endian. So I want to be able to make sure that I'm reading the bytes correctly, and then also I'm converting between bytes into different width data structures. In this case. Or data types, I should say. In this case, I'm converting bytes into 32-bit floating point numbers, and so I'm using the byte order crate to do that. But the feedback was that I didn't need to do this extern. So, okay, great. I'll get rid of that. The other bit of feedback was that I was using this clone on write enum, and I thought I was being clever here, and it kind of is. It's better than what I was doing constructing strings on the heap. And so this is certainly more efficient. But the comment was that that I could generalize this parse record function by just using as an argument, just using a slice of string or a string slice. And so in Rust, Rust has got this really interesting way of managing memory. It's quite efficient. And so a sort of a slice of strings like this, or a string slice, I should say, is a really nice kind of performant and low it doesn't use much memory, and you can pass strings around. And so what I'm going to do is I'm just going to convert that clone on write enumeration and turn that into this string slice, and I can do everything else that I want to do in here. So that should be fine. But now I can see that I've broken something. So what it's complaining about here is that this record string is still a clone on write enumeration, and it should be a string slice. And so the good thing about this clone on write enumeration is that it's pretty straightforward to just turn that into a string slice. Let's have a look. I don't know if it shows us that here. Probably not. But the way that we do that is we just do a reference to it. So that solves that. And I think that sort of fixes our argument there. So we've got rid of clone on write, which also means that we don't need this standard borrow clone on write use at the top, so we can get rid of that. The other thing though that I got back from the viewers was that we built this struct called fits that was going to contain all of the data that we care about, and after we've parsed it. And what I was doing here was I was sort of passing these parameters to fits. So this is kind of like a generic that actually doesn't do what I thought it was you know it's not doing what I wanted. So I'm going to get rid of the explicit sort of template there, and then what I'm going to do is I'm going to get an error. Oh yes, okay. So the data struct was specifying a lifetime because I had borrowed this this array of bytes, and so is it a slice? It's a slice of bytes, right? So data is a slice of bytes, and so you're effectively borrowing the data that this thing points at. And you need to kind of couple the lifetime of these two things together, right? You don't want to deallocate the data you don't want to deallocate the memory that data points at and then still try and reference it. You want to sort of manage the life cycle of these two things together. Now, because I'm using data inside of fits, the fit struct, it's now also saying, but hang on, data, we need to worry about or think about or track the lifetime of data as well. And so the way to do that would be just to specify a lifetime here. And then I'll also need to do that at the fit struct as well. Okay, so that's gotten rid of that problem. Now it has generated some other errors, and that's just because I need to update how I'm using the fit struct here, and then probably the same down here somewhere. Yeah, when I call RenderData. All right, so that's kind of cleaned up the code a little bit, folded in some of the feedback that we had, and so let's just make sure that we can still run it okay. So if I go and open my command line environment and just do cargo run, I'll just make that a little bit bigger for everybody so that they can see it. Yep, okay. So that still works, and that looks good. Awesome. Okay, so what we're going to do is we're going to now start improving our program. So I'm sort of not sure where to start. We either start by trying to generalize what we were doing last time. So instead of hard coding the dimension and the size of the data, I'm going to, or the shape of the data, I probably should call it. Instead of doing that, we should generalize it, and we should be able to read the header and actually understand what that is from the header. So we could start there. We were forging ahead though, and we were trying to render data, and we were going to do some normalization, and I talked about stretching the data as well and then writing it out as an image. And I'm not sure where we should start. I'm thinking what we might do is we might just generalize this first. I think that's probably the best way to go. In which case, we'll need a couple of functions. So let's do a get dimensionality function. And then we'll pass in the fits header. And then also what we'll need to do is the same thing with our x and y here. So we'll be a bit sloppy, and we'll just say get xy, and we'll pull in the same thing. So fits.header. So we'll now get errors saying that these aren't defined, which is fine. But all right, let's go down and just create these. So we'll do function get dimensionality, which takes a reference, well, we'll call it header, which is a reference to this. It's a reference to a header struct, and it returns. And what we'll do is we'll return an option, because we may not actually find that in the header. I mean, it is possible that we get a malformed header or something else goes wrong. So we'll say it's an option of U32, and then we'll just return none. And then what we're going to do is we'll define get xy to do the similar argument, same argument, header. Sorry, I'll just bring that in the middle of the screen. And then we'll do an option but in this case, it's going to be a tuple, I think, and we'll do that. Oh, what am I doing? It'll be a tuple of U32. Oh my goodness, 32. All right. And so this kind of stubs in the functions that we want, and that will return the data that we want. Now what we need to do is kind of unwrap that, right? So an option either gives us something or nothing, and so we'll use the if-let syntax that we learned a couple of videos ago. So we'll go if-let dimensionality equals this thing. Actually, it'll be if-let dimensionality, sum. So if we can sort of, because this if-let statement does the destructuring, so it'll basically, it's like a shorthand for the match for sum. So we'll say if-let sum dimensionality equals that. Then what we'll do is take that code up in here, and then same thing for this. So we're going to have to say if let sum, and then we'll get the tuple. Then we'll have this. Okay. So far, so good. I think. I just had a typo here. All right, so far, so good. It looks like this will compile. So let's just run it. It should return nothing. Great. Anyway, and so what we're going to do is we're going to go, so we can get rid of this, and we're going to go down into get dimensionality, and we're going to sort of implement this thing now. And so what we're going to do is we've got a sort of a reference. We've borrowed the header struct, and so we're going to be able to do if let sum value. And what we're going to do is look up the inaxis keyword. And for those of you that don't remember, what we were doing was we were looking at. That's probably not a good example. Let me find one that. Okay, so what we were looking at was this was the header information, and the inaxis key told us about the dimensionality of the data. Inaxis 1 told us about the size of the first dimension. Inaxis 2, the size of the second, and so on. So, this could be up to 999 dimensions, and in which case we'd have all these inaxis 1 through to 999, right? Depending on how large this dimensionality was. So anyway, and so what we're going to do is we're going to pull that value out, the inaxis value, and so we're going to say if let sum value equals, and then we've got header and data, and we're going to use the get function, which will return a reference to the value corresponding to the key, which is good. And so the key is inaxis. Oh, so if we get that, then we also want to then go if let sum. Hang on a second. What we want to get is we want to take the value, which will be a string, and we want to parse it. And the way we're going to do that is value.parse, and then there's kind of like this shorthand notation, which I think is called a turbo fish, which just sounds kind of cool. And so we're going to do if let, and we'll just give it some. We'll give it a thing called dim or something. But what parse returns? Let me just check. I think it's a result. So we'll say if let dimension equals value parse. Then we know that we're able to kind of unwrap the result and pull out the result. parses this string slice into another type, turbofish. So colon with these angle brackets, which is pretty damn cool. So that's kind of the syntax I'm using there. Anyway, and so hopefully dim will be the actual value we want, so we'll return some dim. Otherwise, and we need to take care to make sure that we're matching all the cases, we'll say none. And then so that should finish kind of this if else, and then what's it complaining about here? Mismatched. I don't know what it's complaining about there. And then otherwise we'll just go else, and then I guess we just, the other option would be none, right? So what this should be doing is it should be saying parse, borrow the header, reference the header. If we can destructure the option and get the value out of it, and if we can parse the value as an unsigned 32-bit int, which I believe is the standard Rust integer type, then we return that int, otherwise we return none. And so that should give us the dimensionality. Now the next thing we want to do is pull out x and y, and so to find that we need to look at two other things that we mentioned earlier, two other keys, inaxis 1 and inaxis 2. And so that's why we're calling it x and y, because we can make some assumptions about how many dimensions to look for. And so in this case, we're going to do something like let mutable x and mutable y equal, and we're actually going to just return integers, so we'll just say 0. And then what we're going to do is sort of something similar. So we'll say if let some, let's call it value, and we're going to look into the header again. So we'll say header.data get, in this case it'll be inaxis 1. So if we are able to get that, then we'll say that x is equal to, basically we'll do a similar thing. So value parse, and then this turbofish. I don't think I'm ever going to get sick of that. And we're going to cheat here and just call unwrap, which is not great, but we're going to do that anyway. And then we'll do the same thing here. So, well, actually, let's just cheat and just copy paste. So instead of axis 1, we'll have 2. That should be sort of what we need. And so in this case, what it's going to do is it's going to try and sort of destructure. Well, it's going to, so get returns this option enumeration. And then we're going to just basically use this if let statement again to sort of pull out the value, and if we can parse it, then we say that y is equal to that. And now we're not doing error handling properly here, but if we can get all of this, then we'll just return some xy. And so this should return the option for us, which is nice, but it's going to look like, I forgot. So it's a tuple. So I need to wrap two brackets. All right, so parentheses. So here we've got something that does get xy. Now if we go back and look at this, what we're going to be doing is finding an axis and then pulling out this whole thing and then trying to turn it into a number. But we've got comments at the end of the string. Let's see what happened. That probably should break. We'll just add some debugging. Add a print line here. I think I know what's gonna. I think it's not parsing the x and y because of the comment. So we'll put in here dim is 2 and x y. with x, yeah, y. So yeah, I'm pretty sure this won't print. Yeah. I'm going to get rid of this processing chunk debugging as well. Okay. Yep, didn't print. So it means we're not getting x and y, which means that these things aren't parsing, which is fine. So that means down in parse record, yeah. So in parse record, what's going on is we were only splitting on equals, and then we weren't. So we were probably getting, we're absolutely getting this 80-byte character, 80-byte string, which is just containing all of this, and so we're trimming at the front and the end. Oops, the front at the leading and trailing white space, and so we'd be getting the comments. So what we'll need to do is go and improve this thing. So we'll need to actually split again for the value. Okay, so let. Okay. Excuse me. Let's say let key equal let k equal records 0. Let v equal records 1. Then what we're going to have to do here is do another split. So we'll say let values, we're going to split value v again, so we'll say let values, which will be a vector of these string slices, equal to v dot split n 2 we'll need to test first. We'll have to say if v contains this pattern, then do this thing. In which case v is going to equal values 0. And then we'll do, this was the key, this was the value, something like this. So, oh no, that's wrong, this has to be immutable. I'm sure there's better ways of doing this. So, so basically we'll say, look, if it contains an equals, then let's split it. And then we'll put the key and the value into k and v. If v contains the slash, then we'll split it again, and we'll sort of override what the v was with the first part of that. So we're making some assumptions here, but it'll be good enough. All right, so that should do the right thing. So let's try running our program again, and it did. So that's great. So it executed this code path. So this obviously was able to succeed, and now it's printing out our dimensions, which is good. All right, so we've kind of generalized that, which I feel good about. We'll get rid of that. And so that's great. So now we've got two interesting functions that we can use anywhere else in the code when we want to get the x and y and the dimensionality. Now what we probably should do is completely generalize that somehow, or at least make it more general, and just, basically, I don't know how we'll do the casting or the actual data typing, but it'd be great to just have, say, like, get key or something, and then for it to just automatically, return the right thing. It would sort of suck to have strings everywhere. I think the joke is that's called stringly typed. But anyway, I would prefer not to do that. It would be great to have actual real types. in which case we could probably be quite robust about it and comprehensive if we went through every single data type that's supported in the spec, if the spec specifies all that, but I don't know. Anyway, for now we're just being pragmatic, so we'll just forge ahead. The other thing that we're not doing is we're not checking this bitpix header value, and the bitpix header value is important because it tells us how wide the data is in the data unit. And so in this case it's -32 means that it's 32-bit IEEE floating point, and so that's really important. And the spec actually does tell us exactly. There was 8 values, I think, in a table, or something like that. Anyway, a number of values that specify what bitpix can be. But we'll just, for now, for most of our test cases, we'll be using FITS data that is 32-bit floating point. So we'll just kind of leave those assumptions in the code. And I've got those in a number of places here to do. You can sort of see. You can see what I need to do. Anyway, and so what we're going to do now is we've got our sort of helper functions here, which is there's still too much hard coding going on, but whatever, that's okay. Now what we're going to do is we're going to basically extend this RenderData function. So the RenderData function was meant to interpret the data based on header values. It's kind of cheating because we're making some assumptions. But for those of you that didn't see the last video, what we're doing is we're passing in the whole fit struct. The fit struct has a data struct reference, a reference to a data struct, and then inside of that is basically the slice of bytes. And so what we were doing was we were pre-allocating this thing called a RenderData vector, and I was using this bang or vec exclamation mark shorthand, and we were basically putting zeros in it. So it's a vector of 32-bit floats, and we were sort of pre-allocating the size. And we were, again, this is another assumption about the width of the data. So we were saying that it was 32 bytes. 32 bits. So it was 4 bytes. It was the same size as the byte. A slice of bytes, but we were dividing by 4, right, for 32-bit data. Anyway, and so we were reading it as big endian data, network byte order, and that's in the spec, and we were using this read F32 into, and that was doing the magic for us. But what we need to do is we need to think about a few things. We need to normalize the data. And then we need to write the data out as a PNG. Now, normalizing the data is going to be a matter of taking all of the values in this, think of it as a sort of like a matrix, right? So you've got this 2D matrix that represent all of the values for the pixels in the array, or the CC. There's a CCD detector or a charge coupled device detector. There's actually a couple of those, I believe. But anyway, and so every pixel will have a floating point value. These CCD devices are largely linear. So as the intensity of the light increases, the value on that pixel will be sort of linear, and it'll be quite large. And so what we're going to do is we're going to have to normalize the data. And to normalize the data, we'll need to know what the maximum value is that we want to display. And what we're going to do is draw grayscale images. So that means we know that the values will be between 0 and 255, right? We're not doing RGB or any of that sort of stuff. And so what we can do is we know that we could build a normalize function that took the value that we need to normalize to, the rendered data, and I guess a reference to normalize data, which means again we're going to have to create yet another vector This is probably not the fastest way to do it. So that's kind of useful. Then the PNG will basically be whatever the normalized data is, basically, I think. And maybe the width and the height. But we've got access to all of that. So I think all we need to do is just say, actually, we don't even need that. Let's just, no, we do need that. Anyway, let's get started. So we'll say let's create the normalize. So let's do function normalize takes u32. Oh, actually, it'll be a float 32. It'll be a vector. So it's going to be, what are we calling it? RenderData. Let's call it data. And it's going to be basically a slice of bytes, and then we've got this other vector which is going to be another slice of bytes. It's not right. 32-bit floats. This is going to be a slice of bytes. And we'll call this normalize 2. Like that. And so basically what we're going to do is we're going to sort of loop through the rendered data, and we're going to basically take all of the data. Well, actually, firstly we need to know what the biggest value is in that data block, right? So we'll say let high equal this works. Okay. So we'll say if I is greater than whatever the current highest thing is, then I'm just going to say 0.0. Okay, and so the thing is, I is a reference, so it'll have to dereference, and then we'll have to do something like that. So this is basically going to kind of just loop through all of the data and work out what the highest value is, and it'll be really interesting to know what that is. So we'll say print line, and we'll just say the largest pixel value is high. Cool. And then write PNG is going to do something. We'll just call it data, and it's a slice of bytes at this point, I think. And then it's not going to return anything, and we'll just, I don't know, we'll just call it. Okay. So let's see what happens if we run that. That would also need to be mutable. Okay, so largest pixel is some tiny little value. That's okay. Let's try running it on another data file. So what I've done is I've downloaded a whole bunch of FITS files, and so I think let's try this one. All right, different value. Let's try 218. Okay. Anyway, so these values are all over the place, but that's okay. I think I like. Yeah, anyway, 3,363. Okay, cool. Anyway, and so that works. And so what we're going to do is we're going to, now that we know what the largest value is, we're going to basically use that to convert all of these values. So the largest one in this case is going to be 3,363.963, or 0.963. We're going to basically squash all of that data down into 0 to 255. So okay, so we'll loop through the data, slice again, and we're going to say for I in data, we're going to basically say that, let value equal, it'll be, I divided by the highest, and then times by the normalized 2. And so this value is going to be somewhere between 0 and normalized 2. If it's the highest, it'll be 255. In the case where normalized 2 is 255. If I is 0, then it's just going to be 0. Anyway, and so that should all be fine. And then we'll basically use the normal data vector, and we'll push to that. Fat fingers. We'll basically do push, and we'll push whatever that value was. And so this will kind of basically just grow, because, was it value? Oh yes, as we'll need to downcast it, right? So it's still a float, so to be in floats we'll say as U8. So this has to be immutable, borrow, mutable reference, which means that this also needs to be immutable. Okay. And so this is going to basically build up this list of, or array of bytes, which is kind of representing our normal data. Okay. It's pretty simple. So let's see if that runs. Yeah, it's slowing down because we're pretty inefficient. I wish there was a nicer way of just saying give me the highest value. This should just be like a. I'm sure there's libraries, but anyway, this is simple. And so anyway, so that's interesting, right? We've got somewhere. Now what we want to do is we want to see if we try and draw this, what are we going to see? And we've got some options for drawing. I'm suggesting that we just use a PNG. I'm making some assumptions here. But we could do anything, but let's use PNG. Now, what I'm going to do is use another crate, so that I'm not going to go and build my own PNG library anytime soon. So there are some really good ones. PNG Rust crate. This was the one I was looking at earlier. And so this Rust crate, I don't know, it seems to be updated fairly frequently. and it seems to be downloaded reasonably a lot, which is great. So it's been downloaded 1 million times. It's got 26 versions. So look, it looks maintained. Let's see how we go. So what I'll do is I'll put that in my cargo toml file, and then I will build again, just see what happens. Oh. Didn't I saved? Maybe I did. Okay, so let's have a look at the documentation for that thing. So how does it reckon we should use it? So we want an encoder. And so what it's saying here is, so we'll need to use PNG encoder, path. So, okay, so we'll need to create a file struct. We'll need to use a file struct, buffer writer, or buff writer. So we're already importing standard FS file. We're not importing buff writer, so we need that. So let's import that, and I'm just going to import that into the in the scope of the function. Okay, cool. Yes. Ooh, gee. So we actually, we want to make this a little bit more extensible, don't we? So we need a path, which could just be a string slice, and that'll be the output path. So we'll just call it output path. And the output path can just be data/output.png. And so I've already got an output PNG here, but we're going to basically overwrite that. And we'll just keep overwriting that. So ideally what we should do is we should parse, this path object here, or this path thing that we created up here, data path. I wonder what that data path has. If it has file name or something, then we could just pass that, right? All right. Anyway, we can do that later. So anyway, we'll just keep overwriting the data/output.png, and we've got a buff writer. And then what do we need? We need to create a path. No, we don't, do we? I don't know. Let's do let file equal, and it's just file create. Oops. Can I just pass a string? That'd be better. Seems to be okay. Yeah, can. Cool. So we create a file, and then what do we need to do? We need to create a. Okay. So we'll do let buffer equal buff writer new file, but I think it needs to be middle. So it's saying the trait bound standard result file system file error is not satisfied. Can I just do unwrap? Naughty. I shouldn't do unwrap because you're basically just not handling errors. It'll just panic if it sees an error. And you probably shouldn't just panic in this case. It probably should do something. Like it should actually, like, I don't know, can we do expect? So we could say couldn't create file, not PNG file. Or something, I don't know if that's probably a better way of doing it. It'll still panic, but at least we get an error. All right, and then we can customize the error. So this gives us a buffer. And so what this means is we'll be writing into this buffer in memory until, and so if we're doing lots of writes, maybe it's a large file or a large image, then we can sort of write quickly to memory and then only write to the file, hopefully in an optimal way in fewer writes, maybe one write, for example. All right, so anyway, and then we need this encoder. So we'll do let mute encoder. And this thing is a PNG encoder. And what does it take? The width. It needs the buffer. And then it needs the width and the height. Right, so we need the width and the height again. So let x and y if some and so we're going to use our getXY again, and okay, so let's do this fits, and it's fits. So rather than just passing in, well, we'll have to do both, won't we? Goodness gracious. Okay. So we'll still need this. So what we're going to do is say it is fits.data.header, oh sorry, fits.header.data, and if we're able to get that, then we can actually start encoding this thing. What am I doing? Okay. And so then we can start encoding this thing. Oh, it's still complaining. Expected header. Okay. And so the encoder does, I don't know what it does. So we'll do X and Y. And then we set the color type and the bit depth. That's pretty cool. So we can just do encoder set well, that's weird. Set PNG color type dot set. All right, let's try that. PNG, and then it's color type, and we want grayscale with American spelling, and then we want to set PNG bit depth, and it'll be 8 because it's grayscale. Neat. Except that doesn't work. So who knows what this thing is supposed to be doing? maybe it's old documentation. So what have we got? Set color, PNG color type grayscale. And then we'll do the same, but it'll be set depth. PNG bit depth 8. Yeah, I'm not sure what that was. I don't know why we can't chain those things, but anyway. So that's a not tested. That's what you get for writing document, examples in doco that's not tested. Anyway, and so if we can get the x and y, then we're able to go and do this. And I think that's all we need. Oh, no. Then we need to do let mute writer equal encoder dot write header, and then expect couldn't write PNG header. All right, so this looks okay, doesn't it? And then now we've got this writer. We can now do writer dot write image data. I think. I guess. I think that's it. So this should actually do the right thing. So we've got this buffer. Oh, we do use the buffer. It claims not to need to be mutable. Let's see. So what we do is we get a buff writer, we create the file on the file system, we create this buff writer. If we can get the x and y coordinates, or the size of the image in this case, we create an encoder using this buffer, and then the x and the y is the width and the height. We set the color to grayscale, the bit depth to 8 bits for grayscale, and then we write the header and write the image data out. Interesting. What is error? Returns true. Okay. So if we get an error trying to write, then we just print couldn't write PNG image data. All right, let's see what happens. Let's see what blows up. Let me just delete this. Let's make sure that it writes okay. Yep, we get a... fantastic. We get something that looks like... Okay, all right. I know what's going on here. All right, so we get an image. So this is literally an image off the Hubble Space Telescope, which is really cool. But what we're not seeing here is all the detail, right? We're seeing some of the image, like some of the stars and some of the brighter objects. And this is, so what this is an artifact of, or result of, is the fact that the CCD detector sort of measures linearly, but the human eye actually doesn't see that way. The human eye sort of sees logarithmically. And so, well, anyway, let me say that what we need to do is we need to bring out the lighter, more less bright details out of the image. And so what we need to do is effectively, instead of just reading the the image data and the sort of light magnitude as a sort of a linear scale, what we need to do is we kind of need to bias towards the lower end of that, you know, the less bright part of the image, and so we need to sort of we need something like a logarithmic scale or something that lets us bias towards the lower end so that we can pull out that less bright detail. And so that's what is missing here. So we're almost there, but what we need to do is when we normalize, we probably need to normalize and stretch the data. And so so what I've been researching is there's an interesting paper I found which kind of talks about preparing RGB images from CCD data by Robert Lupton at Princeton. And now what, I mean, I didn't go through this in detail, but I was just looking for kind of like what function are they using to effectively apply a data stretch. And what are they saying? I mean, if you look at just the introductory part of the paper, it says when CCD detectors were introduced into astronomy 25 years ago, CCDs are approximately linear, unlike the roughly logarithmic sensitivity curve of photographic plates. So back in the old days, olden years, astrophotographers or astronomers would use photographic plates, and they would effectively expose those to the light that was coming through the telescope, and these plates were more logarithmic, and so that was quite a natural way, represented kind of what the human eye sees, because the human eye sees light in a logarithmic kind of fashion as well. And so the CCD detectors just kind of linearly map the intensity of the light to a scalar or a value. And so what we need to do is apply something like a logarithmic curve to that data. And what they were doing though was So let's have a look. Did I open this? Yes. So I was looking at the inverse hyperbolic sine function, and so and the paper references that here. So they basically say where x is smaller than 1, then applying this function to x is much less than 1, and when it's greater than 1, so where it's less than 1, and so it sort of where x is very small, it sort of keeps the intensity the same. Where x is higher than 1 or larger than 1, then it looks like sort of log of 2 times that number. So it's a logarithmic type stretch. And then the other way to look at it is if you visualize it, this is the origin of the graph here. You can sort of see that rather than just linearly interpreting the data, which is all we're doing when we're scaling back down to 255, what we can do is we can apply this kind of inverse hyperbolic sine function to every light point or every pixel, and the magnitude of every pixel, and then we can weight the lower end data to a higher value. So we're sort of going to be stretching or pulling out the lower light in the image, or the lower intensity light in the image. So to do that should be pretty easy. So what we were doing was normalize, and let's call this. Let's say let's give it a very specific name, a sine h, and we should just be able to use the built-in maths functions here. And so what we need to do is we basically need to stretch this. I think it's just like this, isn't it? I think a sine h. And so we're going to stretch I and also the high. So we're basically going to do a stretch of that. And then we'll still normalize it to 255, which is what we were passing in here. And then we'll basically now the normal data will be normal and stretched, or biased if you like. And so if we run this again, let's see what we get. Boom. Wow, look at that. That's pretty. So this image looks like it's the pillars of creation, which is just stunning, and it's kind of, it needs to be swiveled around. So the pillars of creation, if I Google it, you can actually see, I think, yeah, Wikipedia's got some really nice imagery here. So that's what the pillars of creation look like, actually, from the Hubble Space Telescope. It's in the Eagle Nebula. So this is from 1995, so it's an old image. And actually, you can sort of see this is grainy. So this looks like a mosaic of 4 images, clearly. And this one is only a partial image. But you can also see that it's grainy here. It's a lot grainier here than it is here. There's more noise in the image. That's what these sort of light and dark pixels are. And so that looks like the same square. Sort of see how that's also more grainy. So I think we're looking at the same source data, but this one's obviously been touched up and different. There's probably a Hubble Space Telescope palette or a Hubble Space palette that's been applied to this to make it look really beautiful. But I mean, it's stunning, isn't it? And so, hey, we've got an image, and we're now stretching the data. So isn't that amazing? Just the stretch that we applied. If I go back to what we had, which is just the linear sort of linear stretch, or just the linear scale, normalizing it to 255, and I run again, we can see that's what the image looks like, right? So that doesn't look anything like what the human eye would see. But by doing this kind of logarithmic stretch, hang on a second, that won't work. I can actually build and see some really beautiful images. Wow. And it's still not quite right, but we can play with that. I mean, you can just see all the dust, and you can sort of see where some of these new stars are being born here, where I don't know, there's obviously the nebula is being, because nebulae are basically just gas and dust, right? And so they get blown around by solar winds and other things, and so but what you can see is where the stars are kind of being born. Basically, effectively, you know, gravity is pulling all this gas together, and you know, in a large enough mass, and as that mass increases and the gravity kind of increases as well, it will effectively start nuclear fusion, which is, you know, how a star burns and creates energy. And so anyway, you see these tips here where that happens, which is just stunning. Anyway, so wow, that is so neat. So let's just try, I don't know, a couple of other images and see if things still work. So we'll just try one of these ones here. I have no idea what these images are, by the way. Wow, that is beautiful. That looks like a globular cluster, I would suggest. And so again, a mosaic of a bunch of images where that is just incredible. So globular clusters are these really old objects, and they sit outside the galaxy or galaxies. So this would be outside our galaxy in the Milky Way, and they sort of sit in what's called the halo of the galaxy, and they are just hundreds of millions of stars that are just pushed together and actually very dense in the center. So that's, I'm really excited. We're actually getting images that we can process. We're pulling out the data, and we're now stretching the data so we can view it. And I'm really happy with that. That's really neat. And I guess, you know, we're probably almost at time again. So what I'm going to do is I'm going to kind of finish the video here. And what I do at the end of every video is push my updates to the GitHub repo, and I'll put the description. I'll put the link to that in the video description, and any of the other assets that I've kind of referenced today. I'll put those in the description too. And we're getting to a point where we can start actually using this as a program, which is kind of exciting. I mean, there's plenty of testing yet to do, and fixes, and a whole bunch of things. What I might start doing though in the next video is I'll generalize a bit more, and if I get any more feedback, I'll fold that back into the code. And then what I might start doing is timing different parts of the code too, and just get a sense of what's fast and slow, and see if we can just kind of speed this up. I mean, we're definitely not being efficient here. It feels like we're just making multiple copies of the data, which just feels wrong. And so I don't know. There's got to be a better way of doing that. But anyway, and so I'm going to leave it there. I'll leave this image on the screen as a sort of a farewell. Look, if you are an expert Rust programmer, by all means, please be constructive and give me feedback. If you're a newbie like me and you're still learning, then join me, subscribe, and sort of learn. And maybe you can join me or download the code and sort of play with this stuff yourself. And if you like the video, please like it. Don't forget to subscribe if you want to sort of see future videos. I think this is video 7. I suspect we'll have another, maybe 5 or 10 videos. Got plans to build a user interface and a whole bunch of other stuff around this, which would be kind of cool in Rust as well. And I'll leave you with that and see you in the next video. Thanks a lot.